Over the next 3 slides, we will use the graphical representation of the work described in the preceding slide to compare the isothermal expansion of an ideal gas from a volume V sub A to a volume V sub B, initially in 1 step, then in 2, 3, 4 steps, and finally in a very large number of small steps. This will allow us to observe how the magnitude of the work done by the gas changes as the gas expands in more stages, or in other words, as it expands more slowly. So let us quickly review the case of a one-step expansion for an ideal gas under isothermal conditions. Gas is initially constrained in a small volume V sub A at a pressure P sub A under the combined actions of the mass m and the atmospheric pressure. As we remove the mass m from the surface of the piston, the gas expands quickly until it reaches an equilibrium state where its pressure P sub B is equal to the external pressure. In this state, the gas occupies a volume V sub B. Since the gas is ideal and the expansion occurs isothermally, the equilibrium states A and B belong to the same isotherm, represented on the right-hand side graph by the dashed red curve. So we have P sub A equals nRT divided by V sub A, and P sub B equals nRT divided by V sub B. As discussed on slide 5, the work is the opposite of the area shown by the red rectangle and is given by W equals minus P external times V sub B minus V sub A, or minus P sub B times V sub B minus V sub A. Alternatively, we can use the expression for the work given by minus the integral of P external times dV between V sub A and V sub B. Since the external pressure is constant and independent of the volume between V sub A and V sub B, we can take P external outside the integral sign, and we are left with a very simple integration to carry out. Let us compare the one-step isothermal expansion we discussed in the preceding slide to an isothermal expansion carried out in 2 steps between the same initial state A and the same final state B. In the first step, we expand the gas by removing a fraction of the mass m such that the gas reaches an intermediate equilibrium state I, where its volume is V sub I equals 50 liters. In the second step, we remove the remainder of the mass m and the gas expands from state I to state B, where the volume V sub B is again 90 liters. For the same reasons given before, state I is also an equilibrium state, which lies on the same isotherm as states A and B. For each stage of the expansion, the final gas pressure is equal to the external pressure during that stage. So P external 1 during the expansion from A to I is equal to Pi, while P external 2 is equal to Pb. Recalling that the magnitude of the work is the area below the curve P external versus volume, we conclude that a gas does more work during a 2-step expansion than during a single-step expansion, since the total area of the red rectangles is larger for the 2-step process than for the 1-step process. We now extend the discussion to the case of the 3-step and 4-step expansions. In the 3-step expansion, the total mass is removed in 3 stages. At the end of the first stage, equilibrium state I is reached. At the end of the second stage, equilibrium state J is reached. And finally, state B is reached at the end of the third stage. State I and J belong to the same isotherm as states A and B. Again, the external pressures for stage 1, 2, and 3 are Pi, Pj, and Pb respectively. The work produced by the gas in 3 stages is larger in magnitude than that released in 2 stages. The same conclusions are reached when we consider the expansion of the gas in 4 steps. The larger the number of steps, the larger the magnitude of the work produced by the gas.